So yeah, this is the topic of my talk, and it's based on a series of work we have been doing with other physicists and some mathematicians, but it's mostly so far very much inspired by techniques in physics. So I came all the way from the other building to give the talk here. So hopefully we'll try to make it very as understandable as I can. So a brief outline. So first I will talk about B-branes in gauge linear sigma models, and all the concepts will be defined. Then we will talk about I need to introduce the B-branes. Then we will talk about the concept of B-brane transport, which is related to something called window categories, or the so-called grade restriction rule. And again, all this will be explained. Then I will talk about central charge of B-branes. And finally, I will give some example on non-geometric phase, of the central charges. So hopefully this first part serves as a motivation, so you know why you may care about these things. So let me first start defining, so this is section 1, so let me start defining the gauge linear sigma model. So the gauge linear sigma model is a special class of two-dimensional field theories, supersymmetric gauge theories, but for the effects of this talk, I will define the sigma model. This gauge linear sigma model has a quadruple of objects, which come like this. So first is the gauge group, then I will set some properties of this object in a while. Then is some representation. I need another representation of an extra U1. It's the R charge. And I need a superpotential, and I need some parameters. So what are all these things? And you will see how they come together nicely. Okay. So this is the gauge group of the theory. So it's just a compact Lie group, which I explicitly split it this way in some factor H, which is simple, some simple factor, and a collection of U1s. We can not all split in this way, but for effect of this talk, it's easier to fix it that way. Okay, it can have some discrete factors, etc. But we will take this one to simplify things.
Is it H required to be Abelian?
No, just simple. It can be, like, for example, SU2. So also, I will fix here a representation of G acting on a representation on SLV, where V is just some complex vector space. So this is a representation, and I usually restrict it to be land on SLV instead of GLV, because this is what is called the Calabi-Yau condition, which we like so much. You will see why also. This is related to Calabi-Yau, maybe you already can see it. I have an extra U1, which may be a bit mysterious for some of you, but which I call the R charge. So by now it's just, you can think of it as some kind of grading. I allow this R to be not necessarily integer. And what I want for this R charge is that these two actions R and rho sub B commute. Okay? So I have these two representations, the gauge group, and I have some function here from B to C, which is also known as the superpotential. And I want it to be G invariant. And to have R charge 2. This is a condition. So these two conditions on the superpotential. Okay? These are coordinates here. So, and finally, I have this other set of parameters, which are the so-called, in physics, these are called Fali-Heliopoulos theta parameters, which are simply some complex parameters where I identify the imaginary part. So for me, the GLSM will be given by this set of data. Given this, I can construct a two-dimensional gauge theory. If you want,
Phi to the R means phi composed with R. What is the R?
oh, this is because this I mean the Lie algebra when I write this. So this like phi to the weight. This acts diagonally. Sorry, yeah. I'm really sorry. Yeah. Okay. Okay. Cool. Okay. So this, okay. So that's the definition of the gauge linear sigma model, and I will define now what are branes on the gauge linear sigma models. But before, just for you, if you are very unfamiliar with this, just to gain an intuition of what's this thing, you can think of defining the space sorry. You can think of defining this space where this is a moment map of the G action on B. Okay? So this space, and you take the critical point of this W, and for this depends critically on this, where I choose these parameters. So for certain choices, this will be some nice, compact Calabi-Yau, and it's something familiar for you. But for the rest of the parameters, it can be some of the more complicated manifold, even singular. So we will talk about these guys in a while. But first, let me introduce some other definition. So now,
Can you lift the other board?
oh, well, yeah, that's right. All right, very good. Okay, so let me go to now. I defined GLSM. So far it's just a set of objects, of things, and now let me define B-branes on the GLSM. So B-branes on the GLSM, what are these things? They will be specified by two very distinguished data. One of them will be, I call curly V, which is a fourth tuple. And this fourth tuple makes a equivariant matrix factorization on the G and this U1R of W. So I know some of you are very, very familiar with this, but maybe some of you are not so familiar with. Should I define matrix factorizations? Probably yes. So very briefly, just Q, this is some set 2 graded free sim B is a free sim B, maybe B dual module. So for me, I carry just out the rank of this thing, and Q is some odd endomorphism here, so it's odd. And Q square is W times the identity in M. And I have rho Q, and R star has representations of the game, but now on SLM that act on rho. So this R star is same thing. Also, I like to denote the weights. And again, these two must be commuting and compatible with the previously one defined, because this Q depends on the coordinates on B. So this should be compatible with rho V and R, big R, that I put there.
Sorry, so
Yes.
that the definition of X zeta, did you mean that what is the first DW?
Oh, critical points of.
Critical point. Now you assume that is contained in this level set of mu G? Or what is
Yeah.
it?
So this mu is the moment map.
Yeah.
So I take zeta is a level set. So I take this quotient, and I look for the critical points of W, which is a G invariant function.
So X zeta is just this quotient, right?
No, it is I include is the space of the critical points of W inside the quotient.
Oh, that's X zeta.
That's X zeta. Yes. Yeah. Exactly.
W is a polynomial.
Yes, it's a polynomial. Sorry if.
And the
Yeah.
representation, I guess, is in a symplectic group, not just in SLB.
What do you mean?
You have a moment map.
If it's a moment map of the action of rho, the action of the group on B.
Yeah, so it's a symplectic action.
Not necessarily. Oh. Well, let's say
This quotient is like could be interpreted as GFT quotient.
it's a GRT quotient. Sorry, it's like a GRT quotient. Is that okay for you? Or?
Okay.
Or a
Fine. Not a problem.
symplectic quotient. Okay. Okay. Where was
Is that a trivial fact, by the way? I'm just trying to learn that.
G is
The GIT quotient is the same if you think of it as a symplectic quotient? Because this looks like a symplectic quotient.
There's an equivalence to these two, but
I mean, there is an equivalence. What I wrote there is literally what I wanted. Yes. Like for a U1 action, this just, you know, I mean, this thing is just this type of map for a U1 action. Okay. So I want to define, I said, B-branes. So I need this set of data, and I need some extra set of data that usually is not, is sometimes ignored. But in physics, to define B-branes, I need to impose boundary conditions for my fields. So some of them are encoded here, but they are gauge linear sigma models have some other fields that are called vector multiplets, which I don't need to define, but boundary condition for vector multiplet translate in that you have to define another set of data, not only this B, but you also have to take some middle dimensional Lagrangian inside this T tilde C, where T tilde is just the Lie algebra of the maximal torus of G. So you need to take a Lagrangian here, which is non-compact. So this is some Lagrangian with growth conditions determined by some effective potential that we will define in a while. So by now it's just a Lagrangian in here, middle dimensional, and this. So the B-brane will be just this pair. We will talk about this gamma in more detail when I define the central charge, actually. All right.
Did we see the vector multiplet? Is the vector multiplet present in this data up here? Or?
Very, very hidden. But yeah, no. The vector multiplet, in principle, is you can think of part of it living here, like coordinates here, but it will be more complicated to define the multiplets. So what's going on now? Why will I care about such thing like a gauge linear sigma model? So the gauge linear sigma model gives you one interesting thing, that is it lets you explore the full, at least in some cases, the full stringy Kähler moduli of Calabi-Yau, for example. So what's this Kähler? Let's talk now about the Kähler moduli. So maybe here. Okay, here, yeah. So let's go to point 2. So to talk about this B-brane transport. So now things should become slightly more clear. I need to introduce this stringy Kähler moduli. So the stringy Kähler moduli is, in terms of this data, is just spanned by, it's a very simple space. It's just e to the t. It's just, these are coordinates there. These are my coordinates here. So this thing is just C star to the S. However, most of these theories, and this is something that haven't had been completely fully made into rigorous mathematical literature, there are some points where these theories are bad. There are some points here that I can choose of these parameters, which are coupling constants of the theory, where I can have something called non-compact Coulomb branches, for example, and some correlator will explode, and it will be very bad. Like the theory we said is singular there. So there are some complex codimension 1 loci that I need to remove from here. So that's what makes this space actually not so trivial. So if you project, it's a
MK? Is that just for Kähler?
MK, yeah, for Kähler. K is from Kähler.
Where does the effective potential?
Where does the effective potential?
Is that going to be of the superposition?
It will be a function here. It will be a function. We will see it. We will see it explicitly. So it will be a function on that torus. So where was I? Okay. So you have this space, and you can do two things. So one thing is you can project. You can take the real and log map and you can project on, I don't know how to call this, like M, K, zeta inside Rn, Rs. And in general, this thing here will have a chamber structure. So this will look roughly like this, for example. I don't know. So this is Rs. This is like the space spanned by these zeta parameters that are somewhere there that I use, has level sets, and this. So these are n, and this kind of amoeba here is delta, is the remove points. So this usually will have a chamber structure, and asymptotically will be like the unstable loci of this guy. But it's more complicated in general. But you don't care too much for small, like close to the origin, where this thing is kind of crazy. Asymptotically, it's always have like a nice form. So each of these chambers is what we can call it a phase. That's where the phase comes from the title. So analyzing phases is a bit of an art in physics. Like you have to do it. Most of the cases is a case-by-case thing. There's no like a nice recipe that will tell you what is the behavior of the theory at one of these phases. But there are some cases where this thing can be nicely analyzed, and you may be familiar. So if, for example, examples of phases, one way to analyze the phases is by looking at that thing I defined there. So you look at this variety, and for example, if this is compact and smooth, and the SLV, the thing landed in SLV, guarantee that that thing will be actually a Calabi-Yau. If it's a Calabi, that's why it's called the Calabi-Yau condition. So this thing, this is what we call a geometric phase. And you can analyze everything around that point by thinking of a sigma model with target space this. But not in every region this will be so nice. So in some cases, there's some cases where this can reduce just to a point modulo some discrete subgroup of G. So these are usually identified with Landau-Ginzburg gamma orbifold phases. And in many cases where X set is just compact, it's not even smooth, where sometimes you get the so-called hybrid phases, which is like a mixture of these two. But most of the time, you actually don't know what's going on there. You have to do a
Delta is the quotient space.
but remember, with the including the critical points of W inside the quotient, right?
When you wrote Xeta's dot mod gamma, what's dot?
It's like just a point. I mean, you can do the example of the hypersurface. You will get this on the Landau-Ginzburg phase. This will be X zeta. So, but that's not the space you want to analyze. That's the thing. You have to do some work to realize that it's really a Landau-Ginzburg model living there, if you are familiar with this story. So these are some of the nicest. So that's what I mean. That are the phases in the title. And as you can guess, non-geometric is anything that's essentially not of this form.
So you'll tell us what the discriminant locus, where it came from, or are we supposed to just know?
You are not supposed to just know. The discriminant locus, so we have ways to construct it in physics, but in mathematics, the only ways I know is, for example, if you have a mirror, this discriminant locus will be like the singular points on the complex structure of the mirror. like if you have a mirror of the Calabi-Yau, the Kähler moduli will be identified with the complex structure moduli of other Calabi-Yau. If you look at the critical points, at the singular points, that will be delta.
If zeta just goes to a critical value of the moment map, if zeta goes to a critical value of the moment map,
Maybe it'd be helpful to think of it as varying the moment maps in a several parameter family, and then at certain values, suddenly you can't find solutions to that, to where the moment map is equal to zeta.
That works. That works for the, as I said, that works to get like the asymptotes of this amoeba.
Yeah,
if you want the precise thing, you need to do some computations. That I don't know how to do it rigorously. Like I can define some function and say, okay, compute the critical values. But I can motivate it saying, if you have a mirror, if you happen to have a mirror, you identify this Kähler moduli has a complex structure moduli, and then you can look at where the Calabi-Yau is singular. Or you can also look at the Picard-Fuchs equation and see where they are singular. I mean, it's the same. For hypersurface, it's this famous for, let's say, for a hypersurface, this MK is just P1 minus 3 points. So it is this famous conifold point. And these are like the large volume, like the points of maximally unipotent monodromy, and this is like the Gebner point, like an orbifold point. So that's.
Is this supposed to have a description on this side in terms of like the poles of the quantum connection?
That's right. If you have that, yes, you will have the. You also can compute this. Yes, that's correct. You have the fully corrected thing. But that's the thing. You need the quantum connection in defining that whole space, not, for example, around a Landau-Ginzburg point or around a geometric phase. Okay, so where was I? Okay, so what's the point of? Let me say a bit more of this picture. The reason for this, because of this being codimension at least one. I cannot see it here, but I can connect this by continuous paths on MK. So this is not really a wall. It's like a real life wall. You can jump over it. So a consequence of this is if at any of these phases I can make sense of the category of B-branes in terms of something that you are more familiar, then they must be equivalent. So an example here, if you have the category of B-branes, so an example, for let's say in this geometric phase, you will call it this dv cog of x zeta. Well, it doesn't care about zeta, but I'm writing it there. Or in this Landau-Ginzburg, you can have these equivariant matrix factorizations of some Landau-Ginzburg potential, not equal to that other that I'm emphasizing. And here you may have some other matrix factorization on more complicated space. And it doesn't matter they look different, they have to be equivalent as you go because of this fact. So when you have like some category on top of B-branes on the GLSM that I'm denoting like this, just so I'm denoting here these objects, lives there. Life is not so simple, and these things doesn't project. For example, if I have a category associated to a phase x zeta, where x zeta is on one of these chambers, and a category associated to an x zeta prime on a different chamber, these things we know, as I just said, this should be equivalent, but these are not one-to-one maps. These are just projections. So we can say projection zeta prime. But they are not one-to-one. It doesn't go back. You cannot lift it in a canonical way.
G because you're thinking of graph category of B-branes?
It's a very, very suggestive, yeah. But so far, let's say, it's the category of, well, these objects are very clear, but I haven't seen a mathematical definition that includes these guys. So these guys form a category that it's like a derived category. It has nice morphism, but I never seen it defined with this object. So for you, yeah, it's just these objects. It's just a collection of these objects identified up to gauge transformations.
So C is just the category downstairs?
Yeah, like this, for example. As usual, if you can make sense of it, sometimes you may not. I mean, it may be very challenging. You are supposed to have a super-conformal field theory on each point, and therefore there should be categories at each point of boundary states. But okay. So this thing doesn't, it's just projections, and there is a nice thing you can do here. Okay. So there is a nice thing that is, you can take a subcategory. There are some sets of subcategory that for me will be like just some set of these objects, some subset of these objects. I will impose some condition. I will talk about that again in detail on the next section. But they're labeled by some label L, because just to emphasize that there are many, this is not just one choice. There's one choice such that I can say, okay, I put some extra conditions on this object, and now this one have nice one-to-one equivalence. Right? So then now you have to say this this thing here is called, this is the so-called grade restriction of discovered by Herbst, Hori, and Page 2008 in physics, and developed in mathematics by some people that are in the audience, like Ludwig Kaczarko, Ballard, Daniel Halper, Kawamato. So there's many people, but so I named the ones that are in the audience. Sorry for this. Daniel also has some theorems on this, and Matt, which he was there. But, so there is all this mathematical definition of this, at least for some large classes of cases where, for example, where the G is just product of U1s, where G is abelian. This is almost, I would say, I think, completely developed mathematically how to do this. When G is non-abelian, it's more tricky. So this is the grade restriction rule, and these things are sometimes called window categories. These ones here. So the picture to have in mind is that you can take.
Can you give me I've just been sitting here, maybe I know one, maybe I don't. Example of you're saying you have a bunch of compact Calabi-Yaos that are realized as the critical locus
yeah.
of some function on a GIT function.
Yeah, let me give you an example. So let's put. So I will give you the data, and you can. Your exercise is to solve the equations. Oh, I can do that. So take this example, U1, and take B C6, and take row B with these weights. This is the most typical example. Okay, so diagonally on C6 with this. And take W, so call a coordinate here P, comma X, to distinguish the one that has -5. So you can write P F5 of X. So this is homogeneous of weight 5 of degree, right? Degree. And if you take it to have the only singular point of this, the only critical point of this to be the origin, then with this you will reproduce, you can see, I mean, you will reproduce the Kähler of the quintic. So that's one example, the most simple example. So, okay, we go back to this. So the picture to have in mind is you take this universal cover of MK. I will have the picture for this, the picture to have in mind for these window categories. And you take the argument map. So you get some space theta that here is like some torus minus some set. That is if I take argument here. So this is just the image of delta of the discriminant. So this theta will have like a chamber structure with regions, I can call it straight TL. And the picture is for each TL, I can associate a window category. So in order to not, so probably everyone may be very confused. Yeah.
This window category, does it have to do with the window category of Donovan, Paddington?
Yeah, that's exactly.
Those were kind of subcategories of the derived categories of X sigmas, which were generated by some line numbers and things like that. And you're saying that these are isomorphic with the categories of something like that?
Yeah, so every category that's in this board so far, except for this, is all of them are equivalent, right? Every category here are equivalent between them, and at the same time they are equivalent to any of these. Any of these is equivalent.
Just trying to point out that the window category in their work is some subcategory of the derived category of X sigma and X sigma. Not just the, I don't know what you mean by that.
I thought this all was taking place in the derived category. Because in the paper faces of
I'm sorry.
boundary.
The derived category of
They have to use
these categories are, as far as I know, they are derived.
Okay.
For me, they are just the categories of B-branes in the infrared, and they are all equivalent. So I can use this one, for example, of this one. If I have more than one geometric phase, yes, I will have the right category of different geometries. But here I just denote C to emphasize that they don't have to be geometric phases.
What is the T subword? What is it? Yeah.
This one. Defined by this map. I will do a very simple example now, just to have, so for everyone to have a picture of these chambers, okay? So we will do an example that I can draw on the board, which means that one. So thanks for asking about that, because now I don't have to introduce that. So for example, for the hypersurface, let me denote MK. So MK is spanned by this e to the t. So there's only one t, because there's just one u1. So let me write here theta and here zeta. So now this is a universal cover. So I put just the point at infinity very far away, they put the other special point at minus infinity, and I'm just wrapping up this. So you have, I think these are like at pi and at minus pi, some bad points here, these conical points, and the points go all the way. So if you project in zeta, what you get is just a point here. It's just a real line with a point there. So you have these two faces. It's just two. The geometric face where it's a sigma model on the quintic, and the other face, the Gebner points, where it's a Landau-Ginzburg model on this function f5 has a potential with a set 5 has the discrete group acting on it. So that's what the first projection I made. So the relation, the equivalence between these two is what's known in mathematics as Orlov's equivalence. And the other projection on theta, you have like this, right? So these are my TLs. Okay? So this is a very simple example to have in mind. There are other cases, so I will just put it to emphasize also this, this kind of quantum origin of, or kind of physics origin of this delta, which is this so-called Pfaffian-Grassmannian. So here it's a bit more complicated, the data, but just let me by now say that G is U2. So I still have a one-dimensional Kähler moduli. So still MK is dimension 1. But if you write the same picture I did there, what happens is that you have, yeah. So what happens is that you have one singular point here, but you also have some around here that repeats all the way. So the projection in zeta will look like this. But you don't care about categories here. I mean, it's too hard to analyze. You only care about categories here or here, which in this case corresponds to the derived category of complete intersection. Here you get something like a complete intersection in GR27 of seven hyperplanes. And here you get something called the so-called Pfaffian variety in P6, which is some non-complete.
Previous example, what is the group G?
U1. This is this here.
Oh.
This example, it corresponds to this hypersurface example. But you still have these windows. However, there's some extra phenomenon here, this work in progress, but maybe we will not make it to that. But let's not be so pessimistic. Let me now talk about the central charge.
Can you again lift the blue?
Yeah, that's a very good idea. All right. So let's talk now about the central charge. Yeah.
Can I ask you a question?
Sure.
So this Pfaffian-Grassmannian correspondence, is it the statement that the window of the Pfaffian goes to the window of Grassmannian threefold? The window of the Pfaffian threefold goes to the window of the Grassmannian.
Okay, so that one thing. Windows are defined in this projection. So Windows doesn't know about zeta parameter in principle. To go from Pfaffian to Grassmannian, I need to move in zeta. To move from Windows, I move in theta. That was the philosophy of this.
Can I ask an actually stupid question? Why are there 6 parameters? So that's an X vector with 5 coordinates. Okay.
Yeah. Perfect. Very good. At least something is clear. So let's talk about the central charge. So now, central charge. So the central charge of B and gamma is nothing but a function from here actually to mk tilde. That's where it's really a function. You can think of it an mk, but then it's multi-valued. So the central charge for one of these things was derived in the paper we have with Kentaro explicitly, and it takes the following form that looks maybe a bit intimidating, but it's really just a Mellin-Barnes integral. So for the case the group is non-abelian, you have this, and I will explain what is this in a second. Weights of V. So there's some gamma functions. So far, this is just an integral, like on this middle dimensional contour inside the torus, the complexified torus with coordinate sigma, and alpha and beta are weights of these are positive roots of chi of the gauge group, and these guys are weights of this action, of this rho v representation I just put before. And this is the value of r, the weight r, corresponding to this representation. So this is just a number. Here is t, that I can think of t and the weights as living on the dual of the Lie algebra. So when I do this thing, it's just the usual internal product between the dual and the Lie algebra. Okay, so it's nothing that fancy. And the gamma enters in the integral, and the b enters on this function f of v, which is actually a very simple thing. It's just a character. So it's the trace over m of e to the I pi r star. So I need to go all the weights of this function that was defined on the data of b, and e to the minus 2 pi rho q of let me denote like this, rho q of sigma, meaning this means again weights of rho q. So it's just a character. So you can see this whole thing, the only parameter in this whole thing is the Kähler moduli, the phi theta parameters there. And it's an holomorphic function of those parameters. And now, given this, I can give you a more detailed definition of the contour of gamma, which is something I wanted to remark. So definition, I call gamma admissible if gamma satisfies the following conditions. So one condition is that it's Lagrangian inside T, so with respect to the usual symplectic form there, it's just a vector space. and is a continuous deformation of what I call gamma r, which is this imaginary of sigma equal to 0, the real Lagrangian inside here. I'm defining that way. So it's a continuous deformation, and by continuous I mean it doesn't such that it doesn't hit any pole of, let me write this to make my life easier, just big function like this of this integrand. I have a third condition, which is, of course, asymptotically, I want my integral to be this must go to 0 in all asymptotics directions of gamma. So the integral must be absolutely convergent. That's what I mean by this. And the fourth, just when the G is non-abelian, gamma should be Weyl. There is an action of the Weyl group that's remaining here. Even if I go to the torus, gamma should be Weyl invariant. So these are the conditions for gamma to be admissible. And now the proposal is beta is B gamma, or let me, since people, B is grade restricted. And remember, as I said, in the math literature, you usually won't find this gamma, but you will find this B, these B matrices. So the grade restriction has a mathematical definition, is something that only has a condition on this V. So I said B is grade restricted if there exists an admissible gamma sub t for all zeta, which is for all zeta, which are the real part of t, and all theta, which is the imaginary part of t, inside grade restriction, to the window TL, and for all theta in strike TL. So that's by condition for this thing. That's how I can derive this by just looking at the convergence of this central charge. Okay? And this coincides with what had been found on the math literature also. So
where did that cinch come from? Does it come from the mirror map or something?
Oh, this cinch here? Oh, I didn't explain you where all these things come from, actually. All these things come from our papers that we computed using something called supersymmetric localization. What you do is you take a theory in a disk, this on disk. You take this GLSM, as I say, it's a two-dimensional theory, so I don't know if this makes too much sense to you, but you take it on a disk and you put boundary conditions corresponding to a B-brane. And close to the tip here, where it's curved, you do an A twist. So it mixes A and B. That's why there are B-branes everywhere and Keller parameter at the end. So it only depends on the Keller parameter. It's a central charge. It's not a Gromov-Witten generating series or
Do we
something.
want that to be semi-infinite?
What?
Do we want that to be semi-infinite? Or
Yeah, you want here to put a very long flat seed in there. Yeah.
So it projects off.
Yeah. That's the story. So we compute this by using some techniques in physics that are called supersymmetric localization, which is essentially applying the principles of the ordinary localization that you are used, like Katija-Bott, but to a supersymmetric theory. And then so this is what it spit out. And there's no time, but but I want to explain how it relates to what you will associate to central charges on each of the faces, even the non-geometric ones where you can write a central charge, like for matrix factorizations. But if you want the expression for central charges on any face is given by this if you restrict yourself to branes that are well behaved, meaning the ones that belong to this window. So the most complicated, yeah.
So the small t, in this definition, small t is just, where does it live? It's just it's in this t space. So you're saying basically for every point whose imaginary part is in this t sub L, you have a gamma associated to that point? Did I read that?
Right, so for example, so good that we have the picture here. I cannot put that up,
Yeah.
man. It's good that we have, well, I need those pictures. So here, it means I should be able to find gamma for any point, for example, in this path, or essentially any point in one of these regions. So you see all zeta and theta restricted. So there's a single window, a single set of great restricted branes on this.
Gamma live in the same space as this picture, or?
No, gamma is not here. Gamma is not here. Gamma is living
Oh, okay,
here.
sorry.
Yeah.
Okay.
No, gamma is not in this picture.
Okay, thank you.
And the most
What is zeta equal ability?
sorry. Thank you. So let me say the most difficult part to analyze here is this growth condition. So just for dramatic effect, maybe I should, or in order for people to think, okay, you are bullshitting or something, show the form of this A, what this function A looks like. So this function A will look like this in terms of all the data I have. So it looks scary, but every term is like linear. This thing is every term is like either linear or the one that grows the most are like linear times a log. So there's this arctan that looks very scary, but yeah, this is what you have to analyze. As an exercise, you can do it for the hypersurface case. That thing reduces a lot, like a lot in that case. But any other case, it's very complicated. In particularly on that one, on the Pfaffian-Grassmannian is a very complicated one. And there's an interesting phenomena that I cannot talk in detail, but it's part of the works in progress, that here you have some Windows category associated to this path as you expect, and let's say a different one here. But you seem to have a non-trivial one coming from paths. Let me just write. Yeah, so from paths that do maybe another color, so it's not so messy. But you have like paths that do like this. so that go like between this one and this one. So there seems to be an additional T double prime L associated to this path. So that kind of a very special phenomenon of this non-commutative, of this non-abelian gauge linear sigma model. So since people may be hungry, I thank for your attention and I will stop here.